Right, so let's start. Good evening, everyone. So, like, today's talk is about some Russian styled problems. So, I'll mostly be like motivating solutions to all of them, not all, to some of them. And I sent the problem set few days ago, so I assume that most of you have like looked through some of the problems. Also, I sort of wrote walkthroughs for all the problems, so I hope that helps in case we fail to do a bunch of them. So let's start with one of them. Before that, I'll just like say a few things about Russian styled problems in general. So, like one of the aspects of this problem is like you will have really general and elegant type problem statements where like you would expect to have very uh, slick and uh, slick solutions which are like very smart, and maybe you need one or two lines of calculation, and that's basically it. And
What is
you
the
want
meaning of sleek?
slick is as in like smart, sort of like
Okay,
there's just one idea, and you need to, if you identify that, you are done with the problem or something like that. um,
okay,
Also, you'll probably like need low tech stuff like uh, uh, every problem is like generally like thinking in terms of like combinatorial intuition, like you'd expect you'll need to apply local or global principles in some manner to all the problems, but obviously you'll have a twist in most of them. So like um, let's start with problem 6. So I'll uh, like just show the statement real quick. So this is the statement for problem 6. I'll like just let you read it, and then I'll explain it as well. Okay, so let me just like explain the statement. So what problem 6 is telling you is that you have been given a complete graph AN, and on each edge you assign an edge weight. Assign edge weight, and all the edge weights are like distant reals, right? And then you have been asked to prove that there exists a trail of length at least n minus 1, and all the vertices appear in like all the edge weights are in decreasing order, and all the edge weights appear in decreasing order. So does anyone have any issues with like what the problem is trying to say? Also, I'll not be keeping up with the chats, so if anyone has any problems, please just unmute yourself and feel free to ask. uh, I'm
okay. Weights are
assuming
real
like
numbers.
yes.
Weights are
I
real
couldn't
numbers.
get you. Weights are distant reals, yes.
Okay. And what is this? There exists trail.
Okay, trail. Trail basically means a path with repeated vertices. So
Oh,
basically, suppose you have been given a graph like this, right? So suppose you start here. So this to this to this to here to here. This is a path, right?
yes,
Again, if
yes.
you do something like you pick this edge and again this edge, then suppose this was 1, this is 2, this is 3, 4, 5, 6. Then something like 1 to 2 to 3 to 4 to 5 to 6 to 3 is a trail,
Oh,
right?
okay. But
Basically,
yeah, but
path
if you talk about
with the repeated vertices.
okay, yeah, understood.
I couldn't hear you. Your voice broke. Okay,
Yeah,
cool.
cool.
So,
Understood.
does anyone have any ideas for this problem? Does anyone have any ideas they would like to share for this problem? Let's start with
Maybe
n
we
equals
should,
4.
yeah, maybe we should start with a complete graph of some order.
Right. So let's start with the smallest, like on which you can actually do something. Let's start with n equals 4. Let's like randomly assume some weights.
This is
This one
random.
belongs to this one. Right. So like one thing which might appear like very like viable for a starting point is like you uh, start from a vertex and like keep on choosing progressively decreasing weights. So like you start at a vertex, right, and you look at all its edges, and you say you find that 100 is the most maximum edge weight that it that it emits. Then you that edge and the edges from this guy, right? And uh, suppose this guy emits like you look at the edges of this guy which has like edge weights less than 100 and you pick the maximum one. So suppose this guy has like edge weights of 120, 80 and 50. You pick 120, you pick 80, you don't pick 120. uh, and you continue this process. So this might look as a feasible sort of greedy algorithm at first where you progressively pick the decreasing edge weights. But can someone tell me what's like wrong with this? Why does it not necessarily work?
Maybe like we pick that 80 or a edge, and then after that on that vertex, all the costs are greater than 80, then it won't work.
Yeah, that's one thing, right? Because that does not, because this algorithm only tells you that your trail is going to be decreasing, right? But it does not tell you that it has length something. It does not tell you anything about the length. For example, uh, if you started here and you choose the 100 edge, and this guy has all edges more than 100, then your trail is just of path one. Trail is of length one, right? So that's not something we need. So also does like when you are just given the graph, do you have any idea about what the starting point vertex might be? Just without any other information than the thing given in the problem. Can
Maybe
someone
which
maybe
has the
yes go on?
maybe maybe with the highest weight, which has highest weight connected to it.
Right. So maybe let's try this graph. So suppose this is A, this is B, this is C, this is D. Uh, so you go from C to D. In general, that is actually not true. Maybe this example does not show you that, but in general, that is not true. Does this example show you though? C to D to B. This was taken to be 2. Uh, oh, yeah, actually, we are lucky. It actually just tells you, no, you are not. Right, so this example does not maybe show you that. Let's try something else. Uh, one sec. Yeah, whatever. In general, what you just said, like choose the edge, like which has the maximum edge weight, and maybe one of its endpoints is like the best possible candidate for starting position. That is in general false. You could maybe just draw a few graphs and realize that uh, maybe like choosing a graph might be a bit hectic for me now. I'll just like leave it to you to check. So like so one thing we know is like the starting
The
point
voice is
of
not clear.
the starting yes
Voice is
uh,
not coming smoothly. Is that
okay.
my internet issue or something else?
It's not too bad, like we can still hear.
Yeah,
Wait, I'll just
Yeah,
quickly
that's the case. But what happens is that sometimes it stops and then it starts again. So
yeah,
some
one times,
individuals
one
will,
two times it cracked.
yeah. So sometimes
right.
we
Let me
cannot.
just share again. Uh, any better now? Is it any better now? Can someone respond?
Yeah.
Okay, I'll resume explaining. Uh, right. So like if in your graph you don't have like any fixed starting point. That is to say, you do not know what a good starting point is. Then like what like what plan of action should you take if you know that maybe one of the vertices is a good starting point, but you do not know which one is. Does anyone have any ideas?
We can just try everything and find the average.
Right, that sounds good. Yeah. So that's basically what we are going to do. Yes. So that's basically a global idea, right? So what we are going to do is like we are going to do the most stupid thing possible. So like from every vertex, what we do is we we like start a person, right? We from every vertex one person starts, and they follow the algorithm that we described in the previous slide. Right. So the problem is basically asking us to prove that at least one person is successful. Right. So this is a sort of a global argument because you are looking at the path, like we are now going to look at the paths of all the uh, people as a whole, because like uh, this is basically how I like to think about global. It may not be the most efficient way, but like you generally use global when you know that something in a set is good, but you cannot like pinpoint which thing is like specifically good, right? So like we want to prove that at least one of the person have like have like trace a trail of length at least n minus one, right? So if you like appeal to an averaging thing, so suppose in total the persons cover x edges in total, right? So like we can sort of motivate. Now we are going to like I'm going to like show you a claim. I'm like trying to motivate the claim. So like if the person covered a total of x edges, then what's the average edge? Like what's the average number of edges covered by a person? It's like x by n, right? So like you would want this value to be at least n minus one for your global argument to pull through, right? In other words, you would want the number of edge edges to be at least n into n minus 1. Does this figure ring a bell?
But it is like weird to think this way. How can you even think this?
Uh, you mean the global argument?
Yeah.
Does it? Okay, so like what I was trying to say is like uh, you know that first thing first, you do not know which vertex is the best starting point for you, right?
Yeah.
Like if you draw a few graphs, you will realize that you cannot fix a certain vertex. It may not have any special quality as such, right? So we know that some of one of the vertex
Yeah,
is a good starting point, but you do not know which. That
because
so we will
that's
look at
why,
all of them.
yeah, that's why we should look at the whole picture right away, because
Yeah,
any
indeed.
yeah,
Yeah. So like we will look at all the vertices as one, and we will like look at sort of their average. This is what basically global is all about, right? So we assume like the person in total cover x edges, right? And therefore the average person covers x by n edges. Pardon. And hence like we want the average to be at least n minus one. So like, does this motivate a claim? Can anyone like
Can you please
come up
tell
with
that
something?
why the average should be n minus 1?
That's what we want, right? This is sort of a visually thinking, like because the average is x by n. If this was more than at least if this was at least n minus one, then you could like say that hence by pigeonhole, some guy covers at least n minus one edges and we are
Yeah.
done.
Okay. All
This,
right. Okay.
this is yeah, this is sort of like wishfully thinking. So can someone like motivate a name for this? Another way to like motivate the same claim I'm talking about is just drawing out all the algorithms, right, on a small graph. Let's try this. Maybe it becomes more tangible. We'll start with the same graph. Six, eight, two, seven, four.
These are arbitrary weights. These numbers 1, 6, 8, 7, 8.
Yeah, yeah,
Okay.
yeah.
Yeah, that
So
n
like
into n
suppose
minus one was seeming to be like twice the number of edges in the graph in a KN graph.
yeah, that is a very good observation. What does that mean? Like if all the persons cover a total of 2 into n choose 2 edges, what's a natural claim after that? 2 into n choose 2 is the number twice the number of edges, right?
Every edges there is
So
at least two.
not necessarily. Maybe slightly tweak the thing, or maybe at this point, I think we should just try to like draw the path on a random graph, right, to motivate something. So like
Yeah.
suppose we start at A, right? Remember the algorithm once again. You start at some vertex A, you look at all its edges, pick the maximum, suppose it's 100, and then look at the next vertex, look at all its edges, pick the one with pick the one such that it's less than 100 but it's maximum among the rest. Suppose you have like 120, 80, 90, right, and 130. Then you pick 90, right, and then you like keep on repeating the procedure. So starting at A, uh, we go to B. Uh, oh, sorry. We go to C. Um, uh, we go to C, and from C we need to choose like. Now note that from C the edge weights are 7 and 8. Both are larger than 6, so you cannot move. You're stuck at C. Right. Now let's
Oh yeah.
like move it. Let's move
Yeah.
from B. So from B you choose the largest out of 4, 7, and 2. That is 7. So you move this way. Now you reach at C. You look at C, you choose more than 7. You have only one option, 8. So you go to D. Uh,
Wait,
from
shouldn't it be less monotonically decreasing on that? So six C to A नहीं जाएंगे. It should be less than
wait,
seven, right?
yeah, I messed up a bit. One sec. Uh, sorry. Okay, yeah. Let's. We'll probably go to just A. Sorry. Yeah. So like from C you have two choices, 8 or 6. So you go to A, right? And then suppose you start at C, then from C you go to D, and from D you go to you have like two choices, 1 and 2. You take the two path, right? And then suppose you start at uh, D. From D you take the 8, and then you take C to B. That is this. You take the 7. Then you take the 4. Then you take the 1. Uh, yeah,
Then
that's
you again
basically
end up
it.
at D.
Yes,
So
I
this
didn't
was
get you.
correct.
Right. So like if you wait, give me 1 second. Actually messed up the path for
I think the B
uh,
path you didn't write complete. From B to C, then C to A, then A to B, then B to D, then D to A.
yeah, apologies. I messed up that one completely. Just write it once again. Uh, right? So we have B to C, right? And then this was an arrow here, B to C, and then you have C to A, and then you have A to B, and then B to D, right? It's good now, I
And then
think.
D to A also, because one is less than two.
Yeah, sorry. Yeah, I was just being stupid. Yeah, so like this actually works, I think. Yeah, this is good. So, do you have any observations from this graph? Also, keeping in mind this term, any observations from this graph? Look at the arrows of every edge. Does anything seem interesting?
Like in the total number of paths, if a person leaves D, means every path is covered to exactly twice.
Every edge is covered exactly twice, right?
Yeah, and in
That
both the ways also, and like C to A to C that way.
uh, that is the claim I was like trying to send. So like if you look at this graph, right? So like you note that every edge has been like if you like pick a edge AB, then there is a path that covers the edge A to B, and there is a path that covers the edge B to A, right? So like if no, do you understand that if we prove this claim, then we are done with the problem because like this means that the
Yeah,
total
because then we
length
will reach the starting point.
not something like that. That means that the total length, length of the all the persons combined is like two times the number of edges. That is two and
Oh
two
yeah,
is two.
okay, okay. Right, right.
And so average path is like n minus one, and you would win. So does anyone have any ideas for like suppose you want to prove that there is an edge that A1 and A0 are two given vertices, and you want to prove that uh, there is a person that goes this way. Does anyone have any ideas? Suppose this edge weight is 100 for the sake of it.
So maybe we see the other edges connected to A1, and we see
Right.
if there is any edge with a value greater than 100, then I think this would
Right.
be somewhat true. Because
Okay, so like
if that
suppose you have like edge weights of 120, 130, 140. Which one do you pick?
uh, so in this case 120, because if
Yeah,
it
that
is 140, then it will go to 130 according to our algorithm.
yeah, he basically right. So basically the idea is like apply the algorithm previously described in reverse. So like suppose you want to prove that there is a path from A1 to A0, right? So look at all the other edges emitted from A1. Suppose that there is no person with edge weight like more than 100. That means that the person starting at A1 would directly go to A0, right? So there would be nothing to prove in that case. So you'd also assume that you have like edges from A1 that are like more than 100 in edge weight. So suppose there was like 120, 130, and 140. You pick the minimum. You pick the minimum edge weight that is more than 100, but also minimum among the rest, and you repeat the procedure from here. So like you assume that this guy has edge weights of 200, 300, and 400. Pick the 200 thing, and then move on. Right. So note that at some point of time, this algorithm must stop because suppose at some point of time you would have something like you have gotten till uh, AK to AK minus one, and suppose this has edge weight say uh, uh, given number, let's say 6,000, right? And all the other edges emitted from AK does not have a weight more than 600 6,000, right? So the person starting from here would directly go to here, right? And so basically uh, AK AK minus one up till A naught is actually the path of the person starting at AK. So that kind of finishes. Also,
Yeah, and
like
also I
if
think there is one more possibility if it is going back and back and back, and it comes to A naught, then also that is a possibility of ending, right?
yeah, we do not care about like what the kth vertex is because like we just want to show that some person
It ends,
traverses.
right?
Yeah, you want to show it ends, and you also want to show that it like uh, some person's path is actually this. So like if it was not, right, suppose like also this proof is also not very hard that this is actually a path. Like for example, suppose ak minus 1 is again, let's assume a random edge weight, say 100, right? And this is ak plus 2. So, is there a chance that there is, suppose this is 20, is there a chance, wait, let me just draw it here so that it's less crowded. Uh, so suppose this was k minus 1, and this was k minus 2, and this is 100, and this is 20. So is there a chance like something like ak minus 1 has a neighbor with a edge weight greater than 20, let's say 50? Can it happen? Like what I'm trying to prove is like this path hence obtained must be the path of some person. So if it wasn't, then you would have a situation of this form. K is not necessarily the K here. It could be just any other intermediary index, like say L, where L is at most K. So if suppose this edge was 50, right, then the person then the person here would not pick the 100 and would rather pick the 50, right? So that would be a
Yeah, but
contradiction.
then we can start from 50, go to k minus 1, and then to 20.
No, 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 no. Yeah, I'll just like put it in fresh words. So suppose you are like rotating, like coming back, right? So this was ak minus 2, this was ak minus 1, and this was ak, right? So suppose this edge was 100, this edge was 20. What I'm trying to prove that all we need to prove that this path is actually the path of a person previously described, right? So let's like drop the index of k and let's use say L, right? Where L is just to show that L is not necessarily k. L is anything between k, right? So if we have a contradiction, if suppose the path of a person starting at ak is not necessarily this path, then you would have at something like uh, there is a person who like suppose at al minus 1 such that this weight is 20 but he had a better option of going to 50, right? Do you get the point, like what I'm trying to achieve here? But that would be a problem because according to the algorithm according to the algorithm here, so when the backtracking algorithm, when you were at a l minus 1, you would want to pick the edge weight with value more than 20 but strictly small, so you would rather pick the 50 instead of the 100, so you would not go here, you would go somewhere here and then, right? So that would be a contradiction.
Yeah,
So we
that's what I
prove,
said in that way. But I think that my words were not that good, which I chose.
right, so that solves the problem. Does anyone have any questions they want to ask?
I want to ask, like, in this problem, the optimal approach should be like we should take many cases, in a K4 graph.
Like for
Right?
rough work, yeah, you should maybe if you try a small cases that helps in motivating like the two and choose to thing. But like I said, with enough experience you could just like sort of wishfully think like uh, two and choose two means like you could like sort of wishfully think that every edge is covered twice or something. But yeah, some small cases are very useful. You could say on paper try doing it on a K5 as well to like make sure that this is the claim you are trying to chase.
Yeah, because the
Yeah.
claim cannot just pull out with just one graph. We should, if that can only come out with we try more cases.
Yeah, that's maybe up to a person.
Oh yeah,
So
yeah, that's also true. Up to that's depend on person.
so like if anyone does not have any more questions, I'll move on to problem two. Uh,
Okay, move on.
right. Okay. Let's explain the problem. Uh, so the problem two is from Elmo 2020. So it basically tells you that you've been given M cross N board, right? And in every edge of the board, sorry, every cell of the board, you write a number such that every row has consecutive numbers in some order, right? And every column also has consecutive rows in consecutive numbers in some order, right? And suppose that all the cells of the board is like at most s, for some s as a function of m comma n, and you've been asked to determine s. Is the question clear to everyone?
Please repeat. Please repeat.
Okay, so like you are filling up cells of a m cross n board with numbers, right? The conditions you need is like every row must have consecutive numbers in some order, right? So you can have something like 2, 3, 1, 4. That's uh, eligible to be written in some row, right? And in every column also you need to have consecutive numbers in some order.
Okay,
And
so every row must have consecutive numbers in some order, and every column has must have
yeah,
consecutive numbers. Okay, okay.
And is there a condition that all the numbers should be distinct, or they can be same also in two different cells?
Then how can they would be
uh,
consecutive?
I didn't get your question. It's consecutive, so yeah, you need distance stuff. No,
No, no,
do you say
not
like
in one row. Like suppose in one row there is two, and then
yeah,
in
that's
another
allowed.
row,
Yeah, I got your
that's
question.
allowed.
Yeah, that's allowed. Yeah, that's allowed.
Oh, all right.
And you want every cell value to be at most one sec. Yeah, every cell value is at most some function s of m comma n, and you want to find that. So something I think he was asking something like, is it possible that this value has a this value is 4 and this value is 4 as well? Yeah, that's possible.
Yeah, thank you.
That's also something we'll need for like the optimal construction. Is the question clear?
We have to
Yeah,
determine the function.
Yeah, indeed.
Okay, okay.
So like
So
first
they are
things
just
first for this
consecutive.
problem, first thing we are gonna try is like like guessing the answer for this problem, right? And then we'll try to prove the bound. So like for the one sec. Yeah. So like let's try the most obvious case of m comma m equals n, right? So suppose you pick a 3 cos 3 board, right? And let's try something very stupid like say 1 2 3 2 3 1 3 1 2, right? This works, right, for a 3 cross 3 board. Does anyone have any problem with understanding this works, right? So this
yeah,
means that 3 comma 3 is basically 3. So you can like just land a guess that s of n comma n is probably just n, right? Mm,
yeah.
Now like
Seems to be.
let's try let's try maybe something a bit more interesting. Let's say suppose you try m plus nm, right? So let's say we are uh, trying something like 3 cross 9, right? Okay, this is difficult to fit here. Let's just move to the next page. uh, Suppose you are trying 3 cross 9. So what we can do is something like you just do what you did before, right? Note that I'm not trying to prove anything here. I'm trying to understand the answer first, right? Then we can like switch to like proof of bound, and we can like what we did for the 3 cross 3 case was like 1 to stack something like this, and you do the same and just increase the value by 3, right? 5 6 4 and 6 4 5. And for the third cell also you can do something like 7 8 9 8 9 7 9 7 8,
Yeah, so
right?
from this, it seems to be like S m comma n is maximum of m comma n. Like I get an intuition.
Yeah, this is fm comma nm, so it's just mm right here because
Yeah,
s of 3 comma 9 was 9. So yeah. So next thing we are gonna do
you
is
wrote you wrote three S of 3 comma 9 s.
oh sorry, yeah. So The next case we are gonna do is like, so this is also something while doing casework, you go from like small cases to larger cases. So like say you do something like uh, ax comma bx for some x, right? So suppose you are doing something like 6 cross 9. What do? We do the same thing. We copy paste the same idea as before, right? What we do is again we stack 1 2 3, 2 3 1 3 1 2, and do the same for the first row as we did before.
Then we can take the 4, 5, 6 in the first, 7, 8, 9 in the second, 1, 2,
Yes,
3 in the
yeah,
third.
yeah. That's exactly what I'm gonna do.
So maybe like for proving n comma n helps a lot in lot of things. We can generalize from that s of n
Yeah,
comma n, because in these also we are just following that pattern.
Yeah, we can do
You
this
know,
arrangement for any MN.
yeah. So like if you like just investigate a case for this, so you will just understand that f of s of ax comma bx is basically going to be s into a plus b minus 1. You can just do here. For example, it's basically 3 into 2 and 3 into 3. So here it's 3 into 2 plus a minus 1. I'll leave the details. It's easy to figure out with a couple more cases. Right. So like if you want to like maximize this value, right? What can you like say about x? Pick x to be their GCD, and this thing is minimized, sorry, maximized, right? So like for example, if you had something like, let's go to the next page, something like 64, 36 comma 54, right? You could think of it as like 6 into 6 and 6 into 9. That gives you 36 plus uh, 54 minus 6. And you can also think of it as like 18 into 2, 18 into 2 and 18 into 3. So you can think of it as like 36 plus 54 minus 18. So we want minimum s, so you pick 18, basically the GCD. Pick x to be GCD. So we
yeah,
like conjecture the answer to be m plus n minus GCD m comma n. Is everything clear till now? Till now we were just like attempting to guess the answer. Is it
yeah.
clear till now? Okay, so let's move on. So now we are going to like present the proof of the bound. So like uh, so what we're going to do is like we'll try to sort of interpret the consecutive numbers condition in a much more weaker way. So note that consecutive also means that you sweep every residue modulo n in every row, right? And similarly, in every column, you have every residue modulo n, right? So what
Yeah.
this motive is like, we will, for every row, we will like define sort of generating functions, if you may call it, or you can just call it polynomials. Suppose you have a row Ri, right? You define the generating function like the polynomial like this. Where suppose C is a cell belonging to uh, Ri, then you define x to the C. For example, I'll just show you an example to give a concrete idea of what I mean. Suppose I'm trying to one second. Suppose I'm trying to write a polynomial for this row, right? What I will write is,
So a genetic polymer that will generate the numbers in this row.
yeah,
Is
you can think of
coefficient.
it sort of like, so it's,
Okay.
I'm gonna write x squared plus x cubed plus x to the 5 plus x to the 6 plus x to the 7, right? I think you get the point. Okay. So having defined that, and you also know that summation over all Ri of x and, excuse me, and all Cj of x is some common polynomial, say s of x, and we want to prove that degree of s of x is greater than sorry, uh, you
Can you
want to
please
prove
repeat
that.
that step? Sigma Rix, sigma Cj, and
Okay,
please
right.
repeat what
So
R and C are.
sure. So like Ri of x is basically, suppose you are writing R2 of x, right? Basically what you do is like you take the cell value in every cell of Ri and you raise x to the power of that cell value and you add it. So like for R2x, it's going to be
Ah,
x
okay.
squared plus x cubed right?
Yeah, understood,
And
understood.
These
if you
CJ
like,
variables
is
are just
similar.
these variables are
yes,
just what like, these variables are not like real variables. I think we
it's
are just
just like you are just writing for like uh,
placeholder. Like
you could think of it like that, yeah. So like
yeah, okay.
if you sum over all the rows, right, and you sum over all the column like values, what you get is basically just like so basically if you sum over all the rows and all the columns, it's basically a simple double counting argument. So you what you basically get is like C cell x to the C, and you define it using the right. So now, if you like
Yeah.
look close at Ri of x, so note that we said like you could think of the consecutive condition in terms of modulo. So like if you have some, so it's of the form of like x to the k plus x to the k plus one plus up till x to the k plus n minus one modulo. Sorry, not modulo. Just it's of the form this for some k, right? So if you just take the x to the k common, it becomes uh, 1 plus x plus x squared up till x to the n minus 1. So this means that note that this polynomial is fixed, right? The big thing is fixed, right? So this basically tells you that 1 plus x squared up till x to the n minus 1 divides Ri x for every like row, right? So what you get is
Yes.
like, and this was basically one sec. Yeah, this was basically x to the n minus 1 divides x minus 1 into Ri x for all the Ri's, right? And similarly, you get x to the m minus 1 divides uh, x minus 1 into Cjx for all the columns, right? So now if you like sum up all the rows, what that gives you is basically like x minus 1 into s of x is divisible by both x to the n minus 1 and x to the m minus 1, right? And hence it must be divisible by their LCM, which is x to the n minus 1 into x to the m minus 1 divided by x to the GCD m comma n minus 1, right? And this basically gives you your
This is
bound.
clear.
Yeah. Oh, just can you please repeat that bound only in the last page which you wrote?
Yeah, sure.
Degree of
So
S of X.
you want to prove that degree of s of x is this thing, right? You want to prove this.
Oh, why should it be greater than equal to? Shouldn't it be less than or equal to? Because
No,
No,
that's
S
the
is,
claim.
no, like something like suppose s equals 9 works, right? Then s equals 10 also works, but you want to pick the minimal s. Suppose all the like cell
yeah,
entries
I
are
got
at
it.
least 9. Okay, yeah.
Yeah, got it. I got it. Thank you.
So that basically ends the proof. Does anyone have any questions for this?
This genetic function was very good, but how can we think of assigning a genetic function? Is it
So
natural?
like one, yeah, it's kind of natural if you think about it. Like uh,
Yeah, we know
for
genetic
one,
functions, right?
as I already said, it helps you to like think of the problem like in
In
terms of
algebra.
like modulo m comma n. Yeah, but I
Yeah.
mean, generating functions for me it was kind of motivated by the fact that you can like weaken the condition in every row and column to think about like what the problem is basically trying to say is like you need every row to have like all the residues modulo m and all every column to have all the residues modulo m. What's the like what is the how less can you make the entry? So in for those yeah the uh, polynomial argument is quite motivated I think.
Okay.
Any other question? So I'll probably move on to example 3.
Yes.
Yeah. So I'll just explain the problem. right? So once again, we have like a table, right? Rows and columns, and in every cell of the table is like some number written. So what we do is pick largest two numbers in both rows, sorry, in a row. You sum them up, right? It is observed that for all rows, this sum is the same, right? And you observe that for all, it is observed that for all rows, this sum is the same and it's equal to A. And another thing you do is like you do the same thing for columns. You pick the largest two numbers in uh, columns and you sum them up. It is observed that for all columns, this value is the same, excuse me, and this value is equal to B. So you are asked to prove that A equals B. Is the problem statement clear?
Yeah.
All right, so I'll move on to yeah. Let's move on to the proof. So for this proof, like you note that basically in the also like the given table was a square
Yeah, the
table.
condition is quite weird because we both have in all rows also, and then all columns also sum is equal.
Yeah, that's a given condition. And like the board is a n cross n board, right? It's a squared board.
Oh, board is n cross n. Okay, I thought m cross n.
Yeah. So what we are going to try to prove is like note that A and B are sort of symmetric. So like if you prove like some sort of inequalities on A and B, right, they should probably be symmetric. So what we are going to prove is like we will try to prove one of the inequalities A is at least B or B is at least A, right? If you prove one of these by symmetry, you would automatically get the other because like rows and columns are basically symmetric here, right? So suppose
Yeah,
we
yeah.
A cross B with some method, you can use the same method and you
Yeah.
would write row instead of column everywhere, and you would get B is equal to B, right?
I
So
think
that
there
would
is
mean
a
A
lag in your
equal to
voice.
B, right?
Your voice is cracking a lot in the last minute.
Uh, I'll just unshare and share again if that helps.
Yes.
Hello, is the voice any better now?
Yeah, it's not fine. Thank you.
Okay, cool. Cool, yeah. So, like, we will try to prove one of these inequalities, right? So, let's like start by doing the most obvious thing, right? What we do is in every row we mark the two largest values, right? Suppose this. I'm just marking at random. So, what we can assume is like uh, right, so we mark the largest two rows in every column to like sort of introduce a sort of structure.
Oh,
We assume that the ith column has
I think you draw a 6,7 rectangle you drew.
that's not really important. I will not use the picture to be honest.
Okay.
So like yeah, so suppose the ith column has ci marks, right? So what we are going to do is like to introduce some sort of structure and to like what we are going to do is like we are going to draw a graph G with the vertexes as the rows such that you will draw a edge between two rows if their marked cells share a same column. So suppose this is the first row and this is fifth row. So you will draw an edge between 1 and 5 because these two marked cells share a same column, right? So there will be a 1 5 edge. Why we do this is because in general, graphs really go well with like combo flavored grid problems, and we also like helps us to gain a sort of structure on the problem, right?
Yeah.
So is it okay? So like I'll just repeat the definition of G once again. So what we do is basically
Yeah, please repeat.
G is like a graph on the n rows. You draw an edge Ri Rj if marked cells of uh, them share a column. So what is the number of edges in this graph in terms of say Ci?
What
Can
is the?
someone
Can you please repeat the question?
just what is the number of edges in the graph? In the graph G we defined. In terms of Ci, anyone? Okay, I'll just like try to say something. Suppose you consider one column, like right. Suppose this column has like the Ci value as 3. So suppose this, and this are the spots where it has marks. So if you choose any two of these values, it gives you an edge,
Yeah. So
right?
CI C2,
Yeah. So it's basically
sigma
sum of
CI
Ci.
C2.
And if you now note that you also know that summation of all the CIs is 2n, because it's an n cross n board and you are marking two cells per row, right? So you can now estimate this quantity by say Jensen or convexity, and you get this is like at least 1 by n, not 1 by n.
How sigma CI is 2n?
Oh, it's just basically sigma Ci is telling you that how many marked cells are there in total. It's the like basically a double counting process.
Okay. Okay. Yeah.
So you can estimate
Now we
this
will get
value.
a bar
Yeah, you can
on the
estimate
number.
this value by Jensen. So what you do
Yeah,
is
okay.
basically this thing is at least n times 2n by n. Choose 2. That's n, right? So you got like the uh, like number of edges of G is at least n. What does that tell you about the graph? You have an n vertex graph and number of edges is at least n. What does that tell you about the graph? I'll just be back in 10 seconds. I'll just bring water. Yeah, hello. So, like, can someone tell me what does this imply? If you have at least as many edges as vertices, so the graph must have a cycle, right?
Yeah, because all the
Yeah. Yeah.
vertices cannot be just
Right. Yeah.
matched up with this. Yeah.
So, like,
So it
what
is
we're gonna do is
equal
like,
to n. We can claim it is equal to n, right?
no, no, it's
Hmm.
not necessarily going to be equal to m. That is like too bold of a claim. We are just happy
But
with any cycle length.
but how can it be
Yes.
greater than equal to n? We can get according to the definition of G. There is only one edge connecting two vertex, na?
I did not get what you mean.
Okay, sorry, I misunderstood the graph. Yeah, I got it. Yeah, I got it.
Yeah. So now, so like the previous observation tells you that a cycle of some length, say k, exists, right? So now what we are going to do is like we can note that all the rows are basically symmetric. Like the position of any row does not really matter, right? Because you could basically think of the first row to be the fifth row and fifth row to be the first row, and nothing really changes. So we can actually assume that the vertices in this cycle are actually the rows from 1 to k. Further, similarly, since we can like rearrange columns at our will, excuse me, yeah, we can like assume that this like rows have a certain marking pattern. Like you can assume that the first row has these two vertices marked, The second row has these two marked. The third row has these two marked. Right. In general, for I at most k minus 1, the ith row has I and I plus 1 marked, and the last row, suppose this is the last man, the last row, then the last row has kth and first self marked. Right. So do you maybe one row would have been better.
I didn't understand this claim. So,
Okay. So do you understand like the position of rows and the position of columns do not really matter? Like you could think sort of you can like sort of shift the first row to the fifth row and the fifth row to the first row, and still nothing changes in the problem. The problem is still true. Like you can do this relabeling at will. Right. So when you have been given a cycle, we can just assume that the vertices in this cycle are 1 to k. Or you can just like think of it as like numbering the rows as 1 to k, right? When you have the cycle. Also, when you do that, you can actually like sort of enforce a uh, a marking order sort of as well, some sort of order as well. Because like suppose the first row had marked somewhere here and somewhere here, and you can rotate, you can like move this column this side and assume that the mark is here now, right? So you can basically do this relabelings at will. So uh, what we end up with is basically this sort of a structure. I'll just like be more clearer with this. Suppose k is equal to 5. 5, yeah. So this guy has these two marked, 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 and this guy is last, and yeah. Right. So suppose this is the structure we are dealing with. I'll just erase this. Uh, so now is the doubt resolved now? I'll just like move on. So
yeah, I
now
just
note that
understood. You can switch the rows and you can switch the columns. I understood that point, but I'm
yeah,
still not convinced कि this pattern should occur. I mean, what's the proof कि ऐसा pattern आ सकता है?
if like it does not occur, you can. That's what I'm trying to say. You can like move the columns and the rows in such a way that this is enforced, because you can relabel anything as you like.
Okay.
So now this is a sort of a k cross k subgrid, right? You have like 2k numbers in here, and they sum up to ak, right? And now if you like look across the columns, right? So note that again by a sort of an averaging argument, you have like some column has a sum of at least ak by k, that is at least a, right? Do you agree with this? This is basically PHP. But also note that suppose this guy has a sum of at least a, and this sum is suppose x, right? You also note that x is at most b, because b is supposed to be the sum of the two largest guys, right? So this implies b is at least a, and as we said earlier while starting the solution that proving one side of the inequality proves the other, so you're basically done. Is the proof clear to all?
Yeah, this was a tough one than the rest too.
Right. So if anyone has any questions, please feel free to ask. We'll move on to the next problem after that. So I'll move on to the next problem. Uh, okay, let's try problem 7. Uh, so problem 7. Was everyone like fine with the previous problem? So I'll just move on, I guess. So Problem 7 tells you that 110 players uh, play in a. Did I unmute myself? Oh, yeah. 110 players play in a tournament. It is found that among every uh, 55 players, uh, there exists a player who has lost to at most uh, four guys among the 54. Uh, Proof that there exists some guy uh, who lost against at most four among all the 109 teams. Uh, does anyone? Okay, is the problem statement clear?
Yeah.
Right. So few remarks about this problem. So I think personally, this problem is sort of the most Russian problem in the entire set because of like. So one thing that you might at first sight feel like is 100 and, excuse me, 110 and 55 are like 110 is 2 times 55, right?
Yeah.
So you would think something like this is might be generalizable to 2n and n, right? So basically the point of the problem is that 110 is basically a fake thing here. The point of the problem is that you could replace 110 with anything at least 55 and the problem still holds. To be really honest, I do not really have a very good motivation for this apart from the fact that in in a certain like good number of Russian problems you will like find that numbers are not really that important. For example, there's another one in this set as well. I'll just cover that problem after this. So uh, this is one aspect of Russian problems that you should keep in mind. This is sort of a troll problem in that way that
Yeah, I don't think
110.
it needs motivation because sometimes these numbers are really seems like special, but they are not.
No, to
So
be
we
honest,
can just
when I first tried solving the problem, I was stuck on the fact that I did not know how to use 110 with 55 because
yeah, yeah, yeah.
uh, if someone hasn't really seen Russian problems, it's very hard to guess that 110 is actually fake. So, having said that, we'll just like solve for a number x teams in total, yeah, x teams in total, right? And that 55 condition still holds.
Teams or
So,
player.
whatever, like that does not matter.
Okay, okay, okay.
Uh, so, like, what we'll do is like we'll sort of induct, right? The induction hypothesis is suppose uh, the condition of some guy defeating all other. Suppose in every set of k teams, uh, some guy defeating four other guys at most. Sorry, being defeated by at most four other guy condition holds, right? Then it holds for every
K plus one.
k plus one set as well. So yes, but does anyone have any ideas for this first?
Seems like taking a graph.
Yes, go on.
I
And
don't know, man. Like in this type of problem, which I have done some, I usually took a graph in the solution. I mean, it was it.
okay, so if you think about it, so we are basically inducting, right? We are going from k to k plus one, sort of, or uh, another way to think about this is go from k plus one to k, right? What does that mean? Basically, Suppose let's go for the basic case of 55 to 56, and you can just do the k to k plus 1 thing similarly. So, like, suppose let the 56th player be named A, right? So, look at the entire tournament. Let P denote the set of all players. Look at the set P minus A, right? This is a set of 55 players, right? So you know that there is some guy here, uh, named the guy B, who has lost against at most four teams in here. Right. I'll just go to the next page for more clarity.
I think I got a bit of idea. Shall I tell?
Yeah, go on.
Yeah, so there is a B who lost. Who lost to four teams, right? And now we take the other 54 players with A. There is a person in that 55, say C, who lost to four. Now C can't lose to B because if he loses to five players.
Yeah, but
Or
B is allowed five players.
I mean B doesn't lose to C. Okay, no, wait, I confused it. Sorry.
So, like, what I was trying to say is, like, you know that there are B is a guy in here who has lost to at most these four guys, right? So look at the match between B and A. This match happens, right? Can you tell me about the outcome of this match?
Yeah,
Okay,
A
first,
will
like,
win. A will lose.
okay, if A loses, then suppose B loses to four guys here. If A loses to B, then you have something like B loses to four people in the entire tournament. That is a contradiction.
Oh,
So A must win against B, right?
yeah, yeah.
Also note that if lost against three people in here and also lost against A, that's still a contradiction, right? Because again, 3 plus 1, 4. So it loses to at most four people in here. So what happens is that B loses to at most four people. Sorry, B loses to exactly five people, right? A is one
Wait,
of
wait.
them.
How
So
does that give a contradiction? What is the maximum number of that can be that one player can lose? That is four, right?
no, like you have been asked to prove that there is some guy who loses against at most four among the rest 55. We are basically doing for 56 teams right now. Okay,
Oh,
so
okay.
if suppose B loses against three of them, and it also loses against A, then it loses against four teams, right? But four is at most four, so that's a contradiction. So there are exactly four guys, say A1, A2 up till A4 here, such that B loses to A and B also loses to A1, A2, A3, and A4. Right. So, okay, so, and this guy lost exactly five games. So call all such people who lost exactly five games a loser. Right. This is just a name. Note that A sort of induces a loser. Right. You can think of defining a function from every player because to a loser it induces, right? So something like you can say f of A is B. So you note that A1 also sort of induces the loser because if you pick the set P minus A1, again in P minus A1 B loses to A, A2, A3, and A4, and it also loses against A1, right? So A1 also sort of induces the loser B. So you note that every guy, like every guy induces at least one loser B because you could have had like more than uh, two losers in the same like group, right? So you note that what is the minimum number of losers in the entire team? Suppose there were 56 members in total, right? So each one of them induce one loser, and five people induce the same loser. So it's at least 56 by 5, right? Do you get the
Yeah,
bound?
yeah, yeah.
This is basically number of losers is at most, sorry, at least 12. Right. So now you look at the tournament between the losers. We know that there are 12, there are at least 12 losers. Right. So among these 12 losers, right, among on an average, someone loses 12 choose 2 by 2. Sorry. On an average, the number of games people lose is 12 choose 2 by 12. Right. Which is uh, 5.5, which is more than 5. So that is a contradiction. Do you get the understand the argument here? Because we picked a random person A and looked at the group of pairs without A, and from there we find that there is at least one loser uh, B.
Mm. Can you please repeat this contradiction parts? Ki like B lost to 3 and B lost to 4, which you talked about contradictions.
Okay, so suppose this was the number of this was the players without A, right? And this was A. So suppose B was a guy in here who lost to. Suppose B is one of the guys as described in the problem statement, right? Suppose he lost to at most 4 people. Suppose he lost to exactly 4 people, right? Suppose he lost to exactly 4 people and A wins against B, right? Then in total, in the total 56 community, we have lost to how many people? Exactly 4. But that means that he has lost to at most 4 people in the entire community. Hence, B is actually the one of the people described in the like the conclusion statement. So that is a contradiction, right? Because there's nothing left to prove. So next we assume that B has like 3 people, 3 neighbors in here. So not neighbors, 3 people he lost against, and now note that irrespective of the result between B and A, B would have lost at most 4 times. Right. Again, the same contradiction occurs because then we would have like nothing to prove. So we conclude that B loses against exactly 4 teams in this group and also against A, which contributes to exactly 5 losses. Do you get this now?
Yeah.
Right. And then what you do is like quite simple. You look at the tournament amongst all the other players, right? In total, they lose, all the players in total lose 12 choose 2 matches because in every match there is a winner and a loser, right? And on an average, someone loses 5.5 matches, which is more than 5. So there is someone who has lost more than 5 matches, which is a contradiction. Is the proof clear to everyone?
Yeah.
Okay, so if anyone has any questions, please feel free to ask. Otherwise, I will move on to the next problem. Apparently, I cannot create any more frames. Uh, they'll just like maybe make another one. Okay, so I'll move on to problem number 5, I think. Uh, right, yeah. Let's move on to number 5. I'll describe the statement. So, what has been told is like there are 100 girls, right? Each one of them has 100 balls, and each sorry, the balls come in 100 colors, and 100 balls of each color. Prove that we can uh, make some swaps such that every girl has one ball of each color. Okay. So I'll just like repeat what I said. Basically, there are 100 girls. Each of them have 100 balls, right? The balls come in 100 colors, and every like color has 100 balls of that color. So, for example, there would be 100 red balls, 100 green balls, etc. So now we will define an operation called a swap, which is basically two girls, let's say G1 and G2. What they do is like G1 chooses a ball that she has, G2 chooses a ball that she has, and they swap that ball, right? Swap those two balls. That is called a swap. So we need to prove that there is a sequence of swaps such that every girl uh, has one ball of each color, and every ball is used in at most one swap. Right. So you cannot use the same ball for a lot of swaps. You can use the same ball for at most one swap. Is the problem statement clear? Uh, is the problem statement clear? If anyone has any questions, please feel free to ask.
Yeah, it's clear.
Okay, cool. So, uh, like, so, so some uh, notes on how to get started on this problem. So, first things first, uh, uh, this problem is sort of asking you to maybe match every ball with a pair of girls or something, right? In other words, you need uh, for every ball you need to find two girls who would swap them or something like that. In general, it's quite hard to put into words because there is 100 everywhere, and so it kind of gets confusing. Another instant is something like if you have seen enough number of uh, Russian problems, you'd probably guess that some of the there are three objects in this problem, right? Three types of objects in this problem: girls, balls, and colors. You would probably guess that for at least one of the objects, the number 100 is probably like a fake thing. Like, for example, you could have number of girls to be 60 and it would still work. But obviously, you need number of girls to be equal to number of colors, right? Because of stuff. So, so one way to get started is uh, no, so first observation we make is that for any values, we must have number of girls equals to number of colors. So to put things into perspective, what we do is we make a bipartite graph with vertex sets as G and C, where G is basically a girl and C is a color. You draw an edge such that um, girl G has a ball of color C, then you draw the GC edge, right? So note that in total, like uh, okay, so there are 100 girls and 100 uh, colors, obviously. So also, as I first pointed out, this problem should have something to do with matching one object to something else. So that kind of motivates a Hall approach, right? So I'm assuming everyone knows what Hall's theorem is. Uh, so, for example, if you pick like n girls, right? So note that these n girls have a total of 100 and n balls, right? And so, what can you say about the suppose this set of n girls is called uh, say not G, let's just call it A. So these n girls have a total of 100 and n balls, right? So what can you say about the neighborhood of A? Like note that every ball has exactly 100 every color has exactly 100 balls of that color, right? So so suppose n is, let's say, something generic like 38, right? So you have like a total of 3800 balls, right? So if the neighborhood of A was less than 38, let's say 37, then on an average you would have something like more than 100 balls. Uh, on an average you would have more than 100, so some color would have like more than 100 balls of that same color, so that would not be possible, right?
What do you
So
mean by neighborhood? The number of edges in that originating from that.
no, like something like if you have like this is a set and this is your vertex set, right? And this is your set of edges, yeah, then this entire thing is called the neighborhood. Basically, uh, all the vertices in the other set which have at least one edge to this set. So this is
Yeah,
A,
all
and
right, got it.
this is N
Yeah,
of A.
thank you.
So what we came to the conclusion is like if N of A was say something less than 38, then you would end up having some color has more than 100 balls. So that would not really make sense. So you come to the conclusion that N A is 38. Hence, Hall's condition is met, right? So what does that tell you? If you have 100 colors, sorry, 100 balls per color, then you can match girls with colors. Like you can pick a girl G and a color C such that the parents G and C are distinct, and girl G has a ball of color C. But also note that during this proof, did we use the fact that number of balls per color is 100? Do we actually use the fact that number of balls per color is 100?
Oh, yes, because you said
So
that
does
in
the
that.
proof make sense till now?
Yeah.
Okay, so suppose there were 60 balls, right? Suppose there were 60 balls per color, right? So you would have 60 and balls in total. So yeah, what does that tell you? So okay, so suppose you have number of balls per color is 60. You pick 40, 40 rows, so they have a total of 2400 colors. Okay, so tell me what I did before and basically repeat the same argument. What happens now? So you know that if the neighborhood of A is less than 40, right? On an average, some color would have more than uh, sorry, this is 40. Then some color would have more than 60 balls of that same color, which is not possible. So basically, what I'm trying to say is that the number of balls per color is not actually relevant. That is to say that you can basically generalize the proof. Assume that number of balls per color is k, right? Each girl has k balls, right? And do the same thing.
So you
So
mean
what
we
happens?
can generalize it to k, any number instead of 100 to n, right?
Yeah, what I'm trying to say is the matching argument still works with any number of balls, not necessarily 100. as I said at the beginning, if like you could like if you have seen enough Russian problems, you'd probably be able to guess that one of the values in there is probably fake, and it happens to be the number of balls, right? So what happens is like if you pick any n girls, right? They have a total of kn balls, hence they must intersect at least uh, n colors, right? Otherwise, by PHP, uh, some color has greater than keyboards. If you just type with some values like I did before, you can like get it. So what does that really tell us? That basically tells us that if at any instance, like every girl has a fixed number of balls, then you can match girls to colors, right? So you can think of balls in the form of a first set of balls, right? And then you can think of it as like a second set of balls, and then up till 100 set of balls, right? And for every set of balls, you can find a matching between a girl and between the girls and the colors, right? So suppose we do something like you pick a 100 cross 100 board. One sec. Okay, making it 5 plus 5 for now. Right. So what happens is like every girl goes to a column of this row and puts some of her balls in, put one of her balls in in every cell of that column. Right. So suppose this column belongs to G1, this column belongs to G2, this column belongs to G3, this column uh, this is 4 and this is 5, right? So and suppose the colors are like R, B, G, Y, W. uh, let's use some other. So suppose for the first set of colors, G1 maps to R, G2 maps to B, and this is how the colors are matched, right? In the for the first like set of balls. So basically, what we are doing is like we allow the girls to go to a 100 cross 100 board, right? To for some structure sort of, and like every girl puts balls in a particular column, and we put the balls in the rows such that you like follow the matching, which we just obtained by Hall, right? So for example, in the second thing, G1 is G1 is matched with B. This guy is matched with R. This is matched with G. This is and Y. And suppose I'll just randomly fill it up. Uh, Y, W, R, Y, because the matching can be basically anything. Right. So I think, yeah. So suppose at the end for a 5 cross 5 code, suppose you end up with something like this. So does that? So now, can you think of something that helps you to like incorporate the swaps in a good way? So suppose the board such hence obtained is like called uh, M, just a name. Suppose the board hence obtained is called M. So can you think of something that helps to like sort of incorporate the swaps in a good way? Note that what we want is every column to have distinct entries in terms of colors, right? What we have right now is every row has distinct entries in terms of colors. So what does that motivate? basically, if you look at since like we're out of time almost, so I'll just quickly wrap this up. Right. If you like, solution is almost done anyway. So like, if you look at M transpose, right? Transpose is basically rotating the board. So what we are like planning to do is like we have uh, the columns have repeated entries possibly, right? But the row, what we observe is that the rows have all distinct entries. So what we do is like we will rotate the board, right? We will sort of rotate the
Is
board
it necessary that the rows should have the distinct entries?
because matching, that's what we, that's what happens if you match them. Because what we proved is like for every set of balls, there is a matching from the girls to the colors, such that girl G has a ball of color C. So you pick that matching for the first set of balls, right? Suppose
Okay.
this was
Yeah.
as pointed out. So now what we do is we rotate the like the matrix or board, whatever you call it. In other words, you do these uh, sort of like, sorry, you write it at this location R, okay, RPGWY, uh, BRWGY. I should have probably stuck to normal, like numbering names for colors instead of like English alphabet letters. R, P, W, Y, G, and W, R, Y, G, B. And whenever they are different, you basically swap those balls, right? So, for example, you swap these guys, you swap this guy with this guy, right? So basically you swap aij with aji for all I not equal j. This makes for 4950 swaps, right? Also note that every ball occupies exactly one location in the square, right? Hence every ball is exchanged at most one time. So that basically concludes the problem.
Yeah. Okay.
Does anyone have any questions? We'll probably not have time for another problem, so I'll basically end here.
Yeah,
It
we
was a
will.
great session. It was a great
Yeah,
session.
your speed was very good. Yeah, that's why we did 4 5 problems in a row.
Right. Yeah. Thanks everyone for attending.
Yeah, thank you.
Uh, can you please tell us source for more Russian problems?
Just like
Combinatorics.
browse Russian Olympiad. Uh,
All right. Yeah. Thank you.